You've been through several units in which you have dealt with equilibria. First, we introduced the concept of equilibria, and then we applied it in the environment of acid solutions or base solutions or salt solutions that have acidic and basic properties. From there, we're going to go into this chapter and this unit where we're going to be looking at other environments in which aqueous solutions play a big role. This unit is divided into two main categories. We've got homogeneous equilibria, and that will be our first 8 learning objectives. And then we will look at heterogeneous equilibrium. We will see environments where a solid will form from solution. Our first learning objective is to learn about buffers. We need to identify what a buffer is and the necessary components that make up a buffer. This is what a buffer is a solution which resists change to pH. So you create this solution, and if you add an acid or you add a base to the solution, the pH will not change very much. It will resist change. This is the recipe in a sense. What is in the solution that makes it a buffer? It needs to have a weak acid and its salt, or a weak base and its salt. But let's look at what I mean by that. If it's a weak acid and its salt, the salt is, take a weak acid, and I want to take a weak acid and write in this space right here, HF for example. If I take that weak acid and I were to think about what its conjugate base is, that would be F minus. And then if I were to create the salt from that, I would need to add an ion with it. So a counter ion like a cation, NaF, would be a salt containing that weak base. So a buffer consists of a weak acid and the salt of its conjugate base. It could also consist of a weak base and its salt. So let's think of a weak base. Ammonia is a weak base. If we were to think about its conjugate acid, that would be NH4+. Well, I can't go and obtain some NH4+ off the stockroom shelf. I need to obtain a salt that contains that ion, so I put a counter ion with it, a negatively charged ion, for example, and we would have, and I shouldn't say for example, it has to be negatively charged, but it's chloride for an example. There would be a salt. So we have a weak base and its conjugate acid, salt. That would be a buffer. So here's some examples besides the ones I already gave you. If I took acetic acid, and that's what this substance is, acetic acid, and I were to consider its conjugate base would be, remove that proton right there. And that would become the anion, which is its conjugate base. And the salt would be, well, let's put a counter ion with that. Let's put a sodium ion, for example. So that is a weak acid and its conjugate base, salt. We often write it with this slash like this, where you write the base first and the acid second. That is a standard way of writing a buffered solution. Now, I've already given you that example on the previous slide, and it too would be, you write the base first and the acid second, would be a standard way of writing that buffered solution. Here's an example of something that is not a buffer, but often students think that it might be. If I had a solution containing HCl and sodium chloride, well, this is an acid. This is its conjugate base. This is its salt. So it's an acid with a conjugate base, salt. But this is not a weak acid. It is a strong acid. And as a strong acid, it cannot be used to make a buffer. Now let's have you consider this solution. We've got a solution containing this substance and this substance, and it's not a buffer. It has a weak base in it. It has a salt containing an acid. Why is that not a buffer? Think about it and choose your answer. Well, if you said number 3, then you're correct. They're not conjugates of each other. While CH3, NH2, methyl ammonium or methylamine, is a weak base, and while this is a acid, a conjugate acid of a weak base, it is not the conjugate acid of this weak base. Therefore, this cannot be a buffer. Now this is a buffer, and this one throws students very often. We have sodium hydroxide. Well, what is sodium hydroxide? It is a strong base. And we have HF. It is a weak acid. It certainly does not constitute the components of a buffer. But acids and bases react with each other, and let's consider the reaction that will take place. The OH minus of the base will react with the acid. A base reacts with an acid to form F minus and water. So if we look at the amounts that we have 10 milliliters of 0.1 molar, and we have 25 milliliters of 0.1 molar. We have a little bit of this, comparatively, and a lot of this. So what will happen? Well, this OH minus will react with the HF and produce some of this. It'll all go away, and we will have a little less of this and some of that. And what do we have? We have in solution a weak acid and its conjugate base. Therefore, we have a buffer. So when you have a reaction between a strong and a weak, and it undergoes a neutralization reaction, if the amounts are just right, it turns into a buffer. Now, we will talk about this a whole lot more when we get into titrations. So this is just a reminder, when we get to titrations, we'll talk about creating buffer solutions in the course of that, and that won't be for a few learning objectives down the road. So buffers are what we call a common ion situation. What does that mean? Well, a common ion is when you have dissolved two substances into a solution, and the two things that you are dissolving both contain the same ion. That would be a common ion solution. So if we were to take HF, an acid, and dissolve in there NaF, so we've placed into a flask both these things, what would be the common ion? What do they have in common? Well, they both have F minus in them. So we know that when we place HF in water, it, to some extent, because it's weak, will produce some of the F minus ion in solution. We know that when you dissolve sodium fluoride, it 100% dissolves. It's a nice soluble salt, 100% breaks apart, and we end up with some F minus. So this is a common ion situation. So let's think about this. This is a question for you to answer. If you have this reaction happening, and you add some sodium fluoride in which there is some F minus, the question is, what does that added F minus that we see right here, what does that added F minus do to this equilibrium? Does it shift it to the right? And when you shift this reaction here to the right, we would say it increases its ionization. Or does it shift it to the left? And if it shifts it to the left, we would say that we're decreasing its ionization. Well, if you said decrease in the ionization, you are correct. You are increasing the amount of this. The Chatelier's principle says when you add a product, the reaction will shift left to try to use up that added product. So this shift is known as the common ion effect. The F minus is a common ion. Shifting it to the left is a common ion effect. And this is in a buffer always what happens when you add the salt that contains the conjugate base. For example, you will decrease the ionization of that acid, and you will have in solution a fair amount of both the acid form and the base form of that buffer. So this ends our first learning objective. We have completed the idea of what a buffer is, what it does, what its components are, and then we're going to start going into calculating the pH with our next learning objective.